Thanks very much for the opportunity to present. I checked several times and was given the green light not to talk just about what I'm doing here, for reasons I'll explain in a minute, but to talk a bit more about why I have ended up here and some of the interesting things that I've been very lucky to work on the way. I just put these two slides up because I think this is quite a nice summary of the kinds of perspectives that I like to share with as many people as I can, which is that the possible trajectories that we're on. This is actually a slide from the end of The Hitchhiker's Guide to the Galaxy. Everyone knows the story probably. And this is Douglas Adams' other book, which if you haven't read it, you've got to read it. It's a wonderful look at some species that we, in some cases, have lost now since he wrote it. And in some cases, we are in the process of saving them. So it's a very, very good book to realize what could happen and what can be done. Now here, I've been very privileged to work on these projects in a role of mathematical modeler, data analyst. This is all about the risks, source risks of future metal supply. This is a paper that just went out a few weeks ago, extending this work to look at a whole series of metals. The previous one was just on 3 very big key metals. This has now extended that analysis and improved that analysis to include 9. And at the same time, I've been working on a quite different project, which was part of this global compendium to address concerns about tailing safety. And this one figure, which I won't talk about right now, is perhaps the key one if you had to put it one, which is showing that 10% of these vital storage devices have had some stability issues, which was one of the things that jumped out. And we spent a lot of time doing statistical analysis of this to make sure that it wasn't coincidence and that there were some trends. So I got to work with some great people. This is Eleanor, who is the first author of these 2 papers, and Daniel Franks, who is the first author of this one. And also David Brereton, who's the editor of this compendium, and there's lots of other SMI involvement. And of course, you'll have seen one other name, which is on all of these papers, which is Rick's. And I really think I should credit one other person, which is this, because this is the reason that I got involved in these projects and I'm here. I took paternity leave from lecturing to look after this thing. So most of the work I did for this was in this kind of state. And as a result of that, I've been gradually going up to working 1, 2, 3 days a week, and now I'm here full time. So the JK has me at my worst, and hopefully I'll get better. Now, all of those projects are all worth an entire seminar of themselves. Unfortunately, we're about to have just that, because there is a presentation day for the Complex Ore Bodies Project, which overarches all of those and some others, many others. And it's thanks to that initiative from Rick and the university that I'm able to be here. And these will all be presented mostly by the first authors, which is even better still, on those days, on the 5th of November, I think it is. So please do register and attend that. And the fact that those are going to be presented leaves me free to talk about some other things today and share some other perspectives on this work. So Nathan gave a very nice brief intro there. I made this map for another presentation, and I do tend to wheel it out just because it makes it easier to explain. So I come from England, obviously, and as fast as I could, moved over to somewhere sunnier and spent a lot of time at these 2 universities in California. And those were the good old days, you know, where they had superheroes in charge and everything was great. Santa Barbara's up here, for those who don't know, and Caltech's up there in the mountains, and it has these wonderful views just from its lawns. And generally, it's quite an inspiring place to spend a few years. And I was in a lab called the Theoretical Astrophysics and Relativity Lab, and it was run by this crazy old guy. He threw these kind of hippie 70s style parties and claimed that there were, you know, people from the movie industry there. And he would always talk about gravitational waves. And this was back in the early 2000s. And everyone kind of joked about behind his back. It's like, the gravitational wave group, yeah, whatever. And my flatmate just down the road is NASA. And my flatmate said he was working on a Mars rover. And anyway, you know, it was a place where people did these crazy things. And you never really thought too much about it. But it's nice to put this map up because years later, these islands, which I'd spent wasted a lot of time sitting on a surfboard somewhere. You can see the Point Break just up there by Santa Barbara, and I would stare at these islands and wonder if I should ever go. I never did, sadly. They're protected areas, and they're protected areas for lots of good reasons, one of which being this bird which is hanging in there on one of these islands, but on the others is extinct or extirpated. So it used to live there and now doesn't anymore. And I got involved with a project investigating the role of this bird in terms of reforestation. So this is the largest island, which has recovered somewhat after it got devastated by grazing. And that's where the bird still lives. Meanwhile, this other island never recovered. So what's going on is this little bird's planting seeds, and there's a feedback loop in this system. And what we want is this island to look like this. And there are a huge number of problems with the question of whether to reinstate this bird. I got involved with one small part of this, which was just looking at the potential value of doing so. So we took a training set, which was the island where we had years of reforestation with this bird present, and we know how many birds there were, and so we built a model using the first island as a training set. And then imagined putting 25 birds into this new island and seeing how they got on. 25 is a bit borderline to recreate a species. Here we have a backup, of course, but what was impressive is that the parameters that fit the first data were very encouraging in terms of reforesting this other island. So this is not a huge time frame for nature, but a very encouraging improvement in the coverage of this island. And this links to this reforestation issue links to another part of the seminar, which I'll come to soon. So I then went back to England from California in December. I would not suggest anyone ever does this. I nearly died from depression. It was dark and cold and horrible. So I eventually made my way back south and ended up here, which is another place that I think, if you've never been there or heard much about it, it's pretty amazing. So these are the Canary Islands, and it's one of the best places in the world for astronomy. Should be looking at this camera over here, sorry. And this is a view from not too far, actually, from where we work. And this is notable for a lot of things. Like, firstly, if you really want to see space these days, you better be on top of a volcano, or ideally outside the atmosphere completely. So that's where the observatory is up there. Oh, and this area here, with apologies to the people on Zoom, this was completely deforested at one point. So there's a coronal forest going around this island, and they lost it. Almost all of it. But since the 60s have managed to restore it, and you can still you can walk through this island and see the places that have not recovered and the places that have, and you can see what could happen if we did nothing versus the potential of what can happen if action's taken. And it's quite an inspirational view. And the other thing that's inspirational about here is this sort of view, which not quite in space, but it feels like it. But the more time you spend in places like this, the harder it is to really care about the other side of the universe, and you start caring more and more about the side that you happen to live in. And this is interestingly a view shared by astronauts, one of which gave a talk here at an engineering department at Santa Barbara and showed this picture and said that this was a quote by Scott Kelly, who spent a whole year up there before he landed back in Kazakhstan. We were discussing yesterday. And this, from space, this is a tiny little protection layer, saving us all from the void out here, lifeless void. And, you know, there's this sort of comment amongst astronauts that they all come back as conservationists. And I think studying astrophysics does have a similar effect. And I quite like just zooming out, further out. So this is from the moon landing. And I like, when I mention this, I like pointing out that they had plans for this rover, for the lander, which is where this was taken from. They had planned how to do that before they even knew how to actually get there. So that's the kind of planning that we need in the current crisis. A lot of time is spent starting from now, projecting 10 years, 20 years into the future. There's perhaps not enough work about saying, well, how are we going to pull this off if we ever actually get there, if we get through the crisis that we're approaching? That's quite nice. You can see the lander in the shot. Now, as a tribute to this, the Japanese went back to the same spot and took a movie recently, which I like very much. And you can also take the same shot from further away now. And the reason I like this is because that's a real movie of the moon going in front of NASA's Deep Space Observatory. You can zoom further out. This was on the way to Mars. They turned around and took a picture back at Earth. And then here's that rover that my flatmate was one of the enormous team working on. Apparently, he wasn't making it up. Of course, if it had just panned around, then it would have seen Mark Watney just sitting there, otherwise known as Matt Damon. We'll come back to him later. But when the sun finally went down at that spot, it took a photo of Earth. And everyone can see it, right? Well, it's in there somewhere. So that's how vulnerable we look from Mars. And you can keep going with this process. And this is a wonderful, wonderful shot taken by Cassini, and that's us where the arrow is just down here. Now, studying my field was galaxy formation. So to get a perspective, what we would really like to do for my field, just as geologists would like to go back in time and sort of see the rocks forming, what we'd like to do is be able to actually get out of our galaxy and look at it from the outside, which frustratingly we can't do. So we actually don't really know what our galaxy looks like. But when you have no mirrors, you can be as beautiful as you like. So they create these artist impressions from time to time. And what we can also do now is, this movie will be a bit clunky, I think. There we go. Is we can imagine being able to fly out of it and seeing around. It's not a commonly known fact that there are dozens of little galaxies buzzing around ours. Now, to start arriving at the title of the seminar, I'd just like to share this. Which is now imagining flying out through what we've observed in space. So this entire screen would fit behind the white bit of your fingernail if you held it up against the sky. And even that is full of very distant galaxies. But if you keep zooming in and keep zooming in, and you keep going, then eventually you do reach a bit of sky where there is no light coming from. And that's because you're looking at it. You're looking at that bit of space at a time when nothing had happened yet. Just a quick word from Douglas Adams as we tried to absorb that. So at this point, the Big Bang has essentially failed to create anything from hydrogen. It's created some helium, a little bit of lithium and beryllium, but it didn't get very far because Big Bang is a really bad description. My colleague Sam Hinton came up with the phrase hot start, which I think is a better description. But like all hot gases, it expanded very, very fast. And as soon as you expand, it cools down and you get no more nuclei forming. So that was the ingredient she had to work with. And where it needs to get is here. That's Charles Darwin, by the way. So a very different kettle of fish. Now, what the universe remarkably has to do is what we'll now see in this simulation, which is one of the last simulations I worked on in detail before I began working in ecology. And this is just gravity. So if you get the conditions just right, in a real Goldilocks sense, and much work is done on this extraordinary coincidence, it would seem, then it won't just expand forever. Some pockets of the universe will have just enough change in density from their surroundings that they will turn around again and collapse. And then still, for the vast majority of those regions, nothing happens. The ones where something happens and you get a galaxy are where they reach this critical temperature, where they reheat to the critical temperature where you can start forming hydrogen atoms, which is about 10,000 Kelvin. It's a very thin band. And once that collapsed bit of universe hits that temperature, you're away. And this kind of thing happens, which is a resimulation, including the gas of a little bit of that. And this is actually pretty old now. So if you look online, you'll see some much more aesthetically pleasing and exciting versions of this. But I like showing this one because it's one of the first ones that actually did this and one that I worked on. But the first author of this work is Alison Brooks. And this was done in a big collaboration. And what we see here is, this is an imagination of a galaxy like ours starting to form. And it will just spin and spin and spin. And you can see all of these are like miniature galaxies that are slowly amalgamating together. So this is one view, other galaxies possibly formed in a different way. What I like about this is as it starts spinning, it's all happening very fast on the computer, but each of these spins is 250 million years towards the end. And you know, it's spinning here and the Earth's in there somewhere by now. And nothing's happening. And nothing happens, and nothing happens, and nothing happens. And then towards the end, you do one lap and you have some life. And then the next time you get round to the same point in the galaxy, you've got dinosaurs. And then the next, you do one more lap, and then you've got humans. So after a very long time of nothing, you get a very, very, very fast. So after the universe has gone through all of this to create what we have here, then you do start to think that the importance of holding on to it all is more important than understanding necessarily all the details of how it happened. You've understood enough to appreciate how remarkable it is. Now, there's a missing step here because we haven't, the answer, of course, to how you complete that move from the two pie charts is that you need one of these. So a lot of my work was on star formation. A lot of all of our field's work is on star formation. That's obviously an entire series of lectures in itself, but we can just marvel at ours briefly. So I like this picture because these are actual sunspots you can hear, not quite, almost with the naked eye here. So just reminding you how volatile this thing is. And there's actually hydrogen. We've got talks here on hyperspectral imaging. And obviously this is a huge, looking at different parts of the spectrum in astronomy is absolutely vital. So you can look at the sun in all these different frequencies. I like this shot because it's got Venus in the foreground. And you have this amazing new image, and what you're seeing is the star at different depths. So there's no surface. What you see is just the last time a photon of that wavelength hits something. And then it hits your eye, or the telescope in this case. And I like showing this one because then you can really get a sense of the scale of these things. So this is essential both to create all the elements via supernovae. So what you have to do is expand the universe, collapse a bit of it again till you make stars. Then you have to explode those and wait for them to form down and cool. And then you've got somewhere where you might start to make a human. So it's really quite a protected process. And all of this is just from a pretty boring star. So this is the thing that this is the graph that we teach on, which I don't have a lot of, which I won't spend time on. But I will switch to the XKCD version because this is just about the physics of radiation, which is very important for some of the other things I'm going to talk about. So stars are up here in the top corner. What we're looking at here is the amount of energy something radiates and its temperature. And you can put anything you like on here. So all the planets are down here somewhere. So Earth's radiating back at 300 Kelvin. Much less, much lower luminosities, but it's still radiating. And in fact, so are all of we. So we're wandering around radiating 100 watts. So we need to take that in at the same time. Otherwise, that's the end of that. So there's this equilibrium here in the planet, which we're in the process of actually slowly destroying, which seems a bit of a shame. But still very, very close accuracy, there's a balance here. So in terms of this picture, which is now looking at the spectrum, all the different wavelengths of light, energy is coming in here and going out here. And it's this difference which allows life to happen. If we were just all, if it was just hot everywhere, then you have lots of energy, but you can't do anything with it. So the plants have worked this out. And they're operating down here at the bottom of this picture and they're taking a very, very small fraction of the energy here. So the total energy we're getting is 170 petawatts, so some ridiculously large number. And this is the energy that the plants generate is also a ridiculously large number, but it's considerably less than the total that's available. So we're in a unique position here that we can actually we've got all of the rest of this curve to use if we want to. And we don't need very much. Now, we're using an awful lot of energy, but remarkably still a lot less than the universe has provided us with. And all of this energy is just coming in the sun from hydrogen, slowly, slowly converting itself to helium, and then on to other elements. They're all just trying to get to iron. Now, the trouble is, that energy we talked about is over the whole planet. Now, how much do we have each of land? Well, it turns out if you do the mathematics, we have about a cricket pitch, which seems like it might be okay, except you've got on your cricket pitch, half of it's frozen over, half of it's tundra, you've got marshes, blah, 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 blah. There's some forest which you prefer not to chop down. So, you know, what you end up with that's actually usable and roughly is the fraction of the world's cropland is more like a football pitch in the middle of that. And whilst that energy is enormous that we have to use, the amount that we can actually eat is not that great. So 1% of the total energy budget doesn't sound horrendous, but for one species to be using that is quite a lot. And actually the energy that the plants generate on this is 400 watts. So if you're producing 100, and 400 is your maximum energy yield if you just farm the crap out of that piece of land and pour phosphate on it and do everything, you know, you're not gonna be able to keep that up for very long. So, you know, for those who know this story of the Martian, you know, he ends up farming potatoes out of his own poo in using his entire habitat as a farm. And we're not really that close to that situation, but we're on the same page as it. So this is, you know, this is very concerning. And science fiction's having fun with this, both in Interstellar, which we'll look at in a minute, and Blade Runner came out recently, which is a similar kind of picture that is not impossible now. So I eventually arrived in Australia on this tour, and on the day I arrived, I gate crashed some friends in astronomy, and they had this on the table, which anyone know what this picture is here? That is a gravitational wave, the first detected gravitational wave. So they were celebrating the discovery, and it was indeed by the crazy old guy and his team. So that was worth the Nobel Prize. Meanwhile, the film that he pretended that he was making, it turns out he really was making, and it was this, which I just mentioned, Interstellar, which is about where the Earth has reached the point of running out of food and is trying to look for somewhere else without much success. Now, you know, much as I like to believe that Matthew McConaughey and Anne Hathaway and Michael Caine are going to save us all, I would prefer to just stay here and avoid the apocalypse. So I was very fortunate to meet a guy called Hugh Possingham, whose photo I should have put up here, who introduced me to Eve, who's on this paper, and all of these wonderful authors that I started contributing to. I promised to mention of urban ecosystems, which was perhaps a bit generous. Yeah, that's right. That's right. Yeah, different Scott Morrison, although he is quite senior in his field, but he is not the Prime Minister. And it was a great privilege to work with Alex Bruskowski, who's an expert on cats. And he takes all these huge big conservation questions, and it basically involves cats in them. And in this case, the cat was the leopards who are living in Mumbai. And what we pointed out to people who are rightly very scared of them is that, well, you could remove the leopards, and then you would definitely not be bitten by one, but then you would have no leopards, which would be sad in a way. And more importantly, you'd then also be overrun by stray dogs, and thousands would die from rabies every year. So that was a counterintuitive sort of result of the mathematical modeling. We also did some more technical papers, and also this one, which I'll come to again in a second, concerning our own behavior. So coming now to where we are here in Queensland, just as citizens, you know, never mind as academics. What's really the situation? What's really the problem? You know, that 100 watts, okay, we're not really that close to eating it all, to eating everything that can be provided. So, of course, the problem is all our stuff. So I looked up some numbers here, some of which I've done more studies of. And the Queensland consumption of energy is pretty prodigious. So just to start introducing these numbers, we said we had 100 watts just to power us. Well, we're already running an average of 1 kilowatt just from using electrical devices. This is average for the population. This isn't even the privileged people or the particularly wealthy or profligate. And of course, we all drive around all the time. So they're same again, another kilowatt. And a kilowatt's like a kettle, a big kettle on full all the time, just keeping our lifestyle going. Now, these next two numbers, which is the shopping and the flying, these are obviously very variable. But this is not difficult to arrive at this kind of number when you consider that. And we'll come a bit about where that energy is coming from and how in a second if we have time. And obviously the flying, you know, at the time I looked up these numbers, this was very typical for all of us, really. And people who are responsible for multiple projects and connected all over the world would be quadrupling this easily. You know, I tried to get some very senior academics to share their itinerary, and they were up for it. But I think by the time I'd convinced them, we were into COVID, and it all seemed a bit inappropriate. But I might come back to that one day when, if it seems like we're really returning to where we were 2 or 3 years ago, which was becoming a bit frightening. So this is this was a really big part of the puzzle. So if you add all these up, you know, order of magnitude, we're running at 100 times what nature is running us at. We're using 2 orders of magnitude more to maintain the way that we live, which is a bit alarming. And this, if you want to create all that by burning fossil fuels, then it's an enormous amount of money, enormous amounts of emissions, hence all the problems that we're aware of. Now, this was where our paper came from, to see if academia was actually, all the people who were writing about stopping climate change were actually doing anything about it, and the answer was no. So we won't dwell on it, but this figure is all the conferences in our survey, and the green bits is where somebody's doing something. It wasn't even that their conference was online or anything, it was just that the conference organizers did have at least some awareness of the problem, so most of them are just completely ignoring it. And a lot of these conferences are about climate change, remarkably. There are a lot of other papers which go into even more detail on this issue actually out there. Now, how can we try to solve this? Well, this is one solution. Now, I always find myself laughing when I look at this, because if there was a sort of alien committee about saving the humans, just as we were trying to save the leopards or the birds on the islands, you know, they would laugh at this. They'd be like, oh, guess what the humans are doing this week? They've had this great idea where they dig up a whole load of metals and precious metals and cut all the trees down and stick them in a field and try to suck the carbon out of the air. Yeah, so in some way, this technologies probably do need to be developed, and we'll see why it's not completely crazy later. But this is not a viable solution, as everyone kind of intuitively realizes, but it is a niche solution for certain situations. So it is very encouraging to see this developing. Now, there is a slightly older technology that if you want to get carbon out of the air and turn it into a fuel and a building material, then nature has solved this one. And you know, it sounds like an obvious statement, but a group here, who we'll come to in a second, have done a huge calculation of unwanted land on the world, which is not currently vegetated or forested. And really, all it's required, no one will charge any rent, no one's going to mind if you just go there and rehabilitate the land. The tropical East Coast apparently is where we live, and that's apparently one of the places that came up in this enormous study using satellite data of where you can actually solve this. And it's not a question of stopping farming or anything. This is land that's been sort of rejected. And the numbers are absolutely immense, which makes sense when we looked at the global picture. When we first started looking at the planet, it makes sense that the amount that you would have from that vast land area would be competitive with what we're producing. And in fact, it's enough to turn the situation around if we really did commit to it. And, you know, I include this, I include just a back of an envelope calculation to people to convince them of 2 things. Firstly, that that's true, and that it's a viable solution, because just planting 1 tree is a ton per year, which is a very helpful amount, as we'll see. However, we were producing nearly 100 tons each as Queenslanders. So the notion which I've heard one very senior conservationist say that they offset their flying around for academia by planting extra trees in their garden. I can't emphasize enough that it doesn't solve the problem of the kinds of lifestyles that we have. However, most of the world, just to introduce these figures, this is the world's population graphed as a histogram against the energy consumption rate. So you'll recall that we're around 10, which is what kind of really off the axis. I've only populated it here out to 20 just to include all the countries, because there are these small nations that have enormous energy requirements. So we're out here somewhere, and pretty much everybody in the planet's down here around 1, and half of those are much less. Now, if you look at contribution to total energy usage, you need to multiply by the x-axis, and then it fills out a bit. So, a lot of people look at a graph like this or some slightly more aesthetic version of it, and they say, well, I'm here at 10. Oh, there's not very many people living like me. Ah, boff, it's fine. We're a minority problem. Well, no, actually, we're a pretty substantial part of the problem. It's jolly lucky for the planet that there aren't many more of us. Now, I made these graphs from data inspired by work by Andrew, who's my office mate at the Dow Center, which is a place that I did a lot of research a couple of years ago. I'll introduce a bit more better later. Now, Andrew's work is about human welfare. So normally I sketch this to introduce it. But here we have this energy on the axis that we just had, same thing, except now it's just in terms of emissions. So they've, which at the time, well, still now, this is more or less the same thing. But a few years ago, it really was very close to the same thing. Getting a bit better now. Now up here is quality of life, HDI index. A lot of us work with this, this metric. So it's kind of what you want versus what it costs you. Now, what's amazing about this graph is that it really rockets up, because this down here, you don't even have light at night, and you probably can't even cook. And so when you can do those two things, your quality of life improves a lot. And then you maybe start traveling around here, and then you get up here somewhere, and then you keep spending more and more energy, but your quality of life does not improve. Now, we said we were probably somewhere around like hundreds of tons, tens towards 100 tons per capita here in Queensland. So we are off this chart. And yet, here is somewhere like Norway, having an even higher quality of life than the USA on quite moderate energy usage. Now, this is the emissions floor over here. So, in order to pull this off, we would all need to be living up here. And these countries need to get to here without going over here. So that is the challenge in one graph. And now there are ways, which is what the second half of the seminar is about, to try to mediate the period where that's not going to happen. Now, the genius of Andrew's work is to split this up, because not everybody lives the same in every country. So once you divide each country into the range of lifestyles and people in there, this gets more interesting and a bit more enlightening. So here's a huge range of lifestyles in China. Now, and it's now pushing them up to the wealthy people in China are, up here with the USA, and the wealthy people in the USA are nearly off the chart, and we presumably, Australia is probably this dot here, spread out, as we've seen, way off the picture. Now, there's a slight catch here. It looks like, utopia is tentatively plausible here. If you go to somewhere like Scandinavia, where it's all frightfully organized and everyone's pretty conscientious, it looks good. Unfortunately, it's not really true. And this is where the shopping tag in one of the other graphs comes in. Because when you include consumption-based, so if I flick between those, this first graph is what we use in our country, and dividing everything by the population or distributing it according to their wealth. Now, if you include what you're importing, then the picture changes, and even the Scandinavians now are out here at high emissions along with everyone else. So this is another issue that the energy, and well, that there is a lot of research being done on this issue. And I think it's something that's very important to bear in mind and has enormous implications for a lot of the work that I'm very privileged to be getting involved in here, in terms of you can sort out everything in where you live, where you have governance, but if you're going to, if all your material is coming in being made by coal in a mine on the other side of the world, or in a factory in Indonesia where they've deforested a whole area to make that possible, then whose fault is it? Well, it's not entirely yours for buying the product, but on the other hand, if we're going to really solve this problem, then we will need to address that very fast. So the good news about that figure, if there is one, is that somewhere in there was a figure for the total emissions of the planet, which is, I think, 33 gigatons, some horrific number. Now, actually, that's about 4 tons per year per person. We are in the ballpark here. So we are starting just from this very simple order of magnitude calculation. We can believe that actually reforestation will mitigate this problem while we're doing all the cool, fancy stuff with renewable energy. So it is a competitive solution. And this is, I just like this comment from the head author of that study, just pointing out that this is not something that requires political engagement. It actually requires all of us. But by all we mean all 8 billion, especially the ones who can spare the time. So coming back to this picture, the long-term solution is to not produce any emissions at all. So the reforestation, everything is just to reduce the harm that we're doing now, because we can't just stop overnight and stop burning stuff. And the good news there is that the amount, even to give everybody the amount of energy that we use, this enormous number, is absolutely minuscule compared to what's hitting the planet. So from that side, the problem is fine. We have more than enough energy just coming from that hydrogen conversion in the sun to do this. And in fact, the IEA thinks that we don't really need 100 terawatts each to be happy. I'm inclined to agree. So there the figure's lower. Now, supposing that we wanted to do this, how much area would that actually require? So I just put the sums up to show that this is an easy thing we can all check for ourselves, and we don't need to, believe the media or any of that problem. You can just check it. Turns out it's pretty big. So for the world to live like Queenslanders, you would need to cover the entire of Queensland in solar panels. But as a fraction of the world's area, that's not too much. And we, of course, don't necessarily need to do that, although we'll come back to that idea later. What about just powering Queensland? Well, to introduce this notion, you can grab solar irradiance for any part in Australia just online by going to the Bureau of Meteorology. And the issue, of course, as everybody knows with this issue, is the fluctuation. But the good news is that this is the energy incident, and this is the time of year. Good news that if you're in the summer, there's an enormous amount of energy to be had here, and that's something we'll just keep coming back at. It sounds like an obvious thing to say, but it's so critical to solving this problem. But the variability is huge, so it's frequently very low. So for an idea, a family, my electricity bill tells me that typical usage is like 14 kilowatt hours in the neighborhood in St. Lucia. So, in the winter, the solar 1 meter squared is not going to cut it. You'll need quite a lot. And the worst day of the year is very bad. So we would need to at least store overnight, which is $6,000 every 10 years. Now, this is starting to become affordable, and indeed people are doing this, and we'll see that larger organizations are already not just doing it, but profiting from it. We'll see that in a second. But from a feasibility point of view, we probably will need to cover the worst week and also the worst month. So these lines are now monthly and weekly averages. So we have a very low average in the middle of winter. You don't think of Queensland winters as being bad, but the difference in the energy from the sun, just from that angle of the Earth, is really substantial and is ultimately the problem. But, okay, fine. Let's say we need to get enough solar in it. We need to balance the books every month. How much is that actually? 50 square meters a resident? Okay, that's not very much. It's substantial, but it's not a crazy number. So it's about the area of this floor, I'd say, 7 by 7. So this can be done. So if we put our map of Queensland back up, how much area does that look like? Well, now we're talking. Now, when I made this slide, most people would see that and say, well, you know, okay, this can be done in principle, but that's a crazily big area. Apparently not. This is a picture of a proposed project in Western Australia. Look at the size of this thing. So let's zoom in. So this is something like 20 kilometers on a side here, probably a bit bigger. And this is a proposed site area to generate energy and convert potentially to hydrogen. And it is indeed almost exactly the annual consumption of Queensland just being produced by that one array. So this really is happening pretty fast. We'll see, I mean, we know as this is a form of mining, and we know from all the papers that I introduced at the beginning, all the expertise we have here, that this is only the beginning of the problem, and there is now a whole host of other issues to solve here. But this is very interesting to see that the things that we talked about hypothetically a few years ago are now happening. Now, I talked about profiting from this. Now, we have this daily, I'm just going to stop that there, sorry. So this movie is just to look at how the sun and how the variability of energy supply is already affecting us. We all pay the fixed price, but this is a movie of the energy market in Queensland. This is the demand on this axis changing, the demand of the whole state, and the price that the electricity is being sold at. And the other panels are just histograms showing some. So we can see the price dancing around here. And this is basically the marginal cost of coal. So it's the cost, what the power stations can sell at without causing financial problems over the long term. So they're all sort of juttering around there. But as the movie goes on, you find that on a very hot day in January, it saturates and people start bidding from other things at 4 orders of magnitude higher price. So this is actually the real world of electricity generation. So the notion that solar energy, which comes and goes, it's exacerbating this problem, but it's not a new problem. We have the mechanism in place already to solve this. And people are profiting from it, and rightly so, because as we'll see, the cost of stored energy versus live energy is so different for all sorts of good reasons. Now, UQ, because of Warwick Solar Farm, is now exposed to that real price. So if we keep our air conditioning on when the sun's just gone down, they might be paying 10 times as much as they were half an hour previously. And as Martin said the other day, you can now be paid for taking energy. Hence, as a leverage against this, we have actually installed a battery here which trades on this system automatically. It has AI in there so that it buys energy, you know, at $30 and then sells it back at $2,000. So the market incentives are in place to store and resell this energy. And even the complex technology that's going into lithium is not a barrier to that. It's already profitable for a large organization and for larger families as well. And you can't help think it won't be too long before it becomes profitable for all of us. You can actually look up this battery and see how it's doing live on this website. So we can have a quick look back at this situation. There is still one little catch, which is seasonality, which I've already alluded to. Now, if you try to pull this off for the whole year, the amount of storage you would need is prodigious. Now, those other papers that I talked about earlier are all about transition metals and how we're running out of them. We're running out of the ones we've already mined. We're going to need to explore for more. This has very worrying implications for the environment in particular. So we don't really want to just solve this problem by digging up lithium and cobalt. Some, but not entirely that way. What would be better is to modify our demand so that we make full advantage of the sun and don't just always expect the energy to be ready where we want it. So the number here we would have required is very large. Now there is another solution. There are many other solutions to storage. The problem is that the battery storage is incredibly expensive. So if you did try to do it this way, you would find this is the cost minimum here. Now, this is happening a little bit fast, I appreciate, but this is the cost minimum and this is the storage required. So it goes shooting through the roof if you try to be more efficient. So this model which I built to find the cost minimum just ends up putting loads more panels down when they're really cheap. Now, at first you say, oh, the model's wrong. But is it? Actually, that is exactly what would happen probably in the free market. And then you would have free energy because you would already be cost optimized to have put more panels down to make it easier to get through the winter. So that means you've got free energy for somebody to do something with. So it would leave so actually the minimum cost solution here would leave 70% of energy unused. Now we would never get to that because as the unused portion becomes higher and higher, as Marcin was pointing out in the research forum last week, then we will, the economics will pay people to take it. Now, I just flashed this up very quickly because a lot of people say, we can ship energy from somewhere where the sun hasn't set yet and cover the evenings. Completely true. So I set up a simple simulation where we would share energy with Western Australia. These are in rugby colors. This is the Western Australia line in yellow here. And it's true, when you run this simple model, it's very clear that the energy will transmit, and that's including the cost of building the line and the losses in the line, to the best that I could find them at the time, talking to people who are actually involved in the project. Now it helps a bit. Sorry, that didn't load for some reason. It helps a bit, but it's marginal. It's marginal. So it would actually be financially viable to make that connection, but it wouldn't solve the seasonality problem, or indeed the daily storage problem entirely. But all that energy, which is becoming increasingly cheap and indeed free, could go into this. So we'll finally come back to the title of the talk at the end, which is that these lines here, this is the cost. This is just one model. What I'd like to do while I'm here is build a better model of this that takes into account all the factors that we're considering, like the energy becoming free. And indeed, in the literature, there are people already doing that. I feel that the way we can attack the problem from the SMI, understanding what we do about the minerals that will be involved, I feel that there's a real opportunity here to give a really big and clear picture of this question, which I've not had before in any of the other institutes, despite the expertise there. The minerals picture, I think, is absolutely essential. In this particular forecast, we're seeing, in a good place like Queensland, we're seeing solar becoming competitive in the next 3 or 4 years. And there's a bonus graph I can sort of show to emphasize why that's the case, maybe. Now, using hydrogen sounds all a bit futuristic, and it does because we don't have anything here yet. But everywhere else in the world, as you can see, is getting going. So Japan is famously really engaging with this. And actually here in Australia, we have a hydrogen refueling station already. The cars are very expensive, but you get free hydrogen for 3 years. In some places, that number will vary, obviously. In California, I was pleased to say, oh, look, here's one in the Canary Islands. In California, I was pleased to see they've got going with this. And there's one in my old stomping ground of Santa Barbara. You definitely need refueling here, I can tell you from having driven down this road. And the deal there is that there are already 3,000–4,000 cars on the road. And once you don't buy the car, you just lease it and you get free fuel. So for people who have the capital, this is already financially incentivized for them. And the concept with this is that it is currently expensive to make hydrogen, but because at some point already, and especially soon, the energy will not only be free, but you'll be paid to take it. And if you can make that electrolysis ramp up and ramp down stably, then this cost could really come plummeting down, as especially in places like here where the solar energy is so abundant. And I guess the last thing to say is people are a bit skeptical, but this is a graph that I made a while ago about another technological revolution. So this is, we're saying 3,000 hydrogen cars. Oh, well, that's not very much. Tell that to people here. So just a few people with cars on the road of any description. And at that stage, everyone's just laughing at them, thinking, oh, that's a crazy idea. We know what happened, of course. And we can play this game with airline travel. If you're in the 30s and 40s, these are tiny numbers. But we know what happened in the end. So this is 600 million passenger journeys per year from an industry that started from zero. And that all happened in a century. We need it to happen faster than that, but we can go to the next example, which we're all familiar with from our own lifetimes, which is mobile phones. So in the 90s, we were joking about this. There were talks about, imagine if, we could all talk to each other without a landline. And most of the people when I was at school, would sort of just joke about this. But it's actually happened. It happened some time ago. So I think I should, Rick's phone's telling me I should stop. So this is just a paper that we wrote, speaking of the vehicles, about electric vehicles. I'm going to have to skip, but just quickly to say that we made some forecasts there, already worrying about whether we'd hit the 2020 targets. We hit them. We've almost hit them in the years. This data will be, this is data that they've got so far, so they'll be way behind on collecting data for the year, and that's where they need to be. So this is, they're actually exceeding all the targets that we used to make models of a couple of years ago before I went on paternity leave. So you take a few months, half a year out to have a baby, and it's amazing how much happens now. But of course, this paper concluded with the issue of the materials, and I should probably just skip through this. This was I'm stuck scrolling through the slides. I knew I'd run out of time for this, but this was a model I built of all the materials involved in the IEA projection here, which I'll just show and I'll maybe go over again. And what it does is it goes forward in time and looks at the increase in material consumption. And what you can see here is as we change to all these technologies, our material consumption increases and our emissions come right down. Now, what we identified in this project was, of course, that this relies on very rapid growth in minerals, hence the project here. And if that mineral supply doesn't come through, which is what this graphic now shows, this new panel here is showing the emissions, and this is showing the altered forecast of what would happen as you're slowly unable to meet these forecasts and you have to substitute with fossil fuels to meet the demands. So these two are inextricably linked, and that is why I'm involved in this project. With this figure encapsulates this work and the problems we have to address, which is so please tune in on the 5th of November to hear more about that. And in the meantime, I'll just leave you with Matt Damon and the dilemma and take any questions. Sorry for running a bit late.
Okay, thank you, Martin. It was a really mind-expanding talk. I mean, it was really quite different and certainly probably raised a lot of questions from the floor. I'm just going to quickly check on Zoom to see any questions that have come in. If anybody does have a question from the floor and they want to get started, if not, I have had, it's very question and answer style. I've had a question already submitted that is kind of revolving around some of the transition that we might be expecting, particularly here in Australia, from coal-fired power stations to the widespread renewable sources. I think you touched on this, but this is from David Esser, who's in our group, and he's just probably keen to understand a little bit more about how we're going to deal with that transition to renewable energies and away from fossil fuels and coal power stations.
Right, well, you can look up a lot of this on the Energy Market Operator site. They actually have a plan in place. One of the papers that was written by the Dow Center just before I left was all about retirement of coal. So there is as fast as some people in the community, many people might want to get rid of it, there is a question about once you have an asset, whether it's better to leave it going and let it naturally finish its life. It's a bit like continuing to run an old car. So letting the coal, letting coal go gradually down, it is possible that there may be an emissions optimum in there. It's a difficult calculation, but the point is that there are people in the electricity system whose remit it is to try to solve this problem, and they are working on it. So the best answer to that question is to go and look at what they're planning and what the anticipated take-up is. But my personal view of this is that the speed at which the cost is coming down is going to drive out fossil fuels faster even than we might plan to do it as a society, because it's becoming cheaper. I think that's it's really on the table now.
Do you think that Boris Johnson's promise is feasible? He's suggested to move to, we're a windy nation apparently in the UK, so we're going to be transitioning to a wind.
Now there was a whole paper about wind which we did at the Dow Center, and I would like to have talked about that, and perhaps I'll do that at a research forum sometime. As for it, because of course it is a huge solution. That place I showed in Western Australia has a wind farm too. So that should have got perhaps more mention as a combined solution. In the UK, it's a pleasure now to be doing these calculations in a place which is so abundant in sun compared to the UK that I tend to get fixed on the solar question.
Martin, so yes, thought-provoking, all that sort of thing. just on this last question, I was at a presentation in the House of Commons a few years ago, and somebody from the coal lobby said the only way to achieve economic, signal is for coal to become a lot more scarce. And so he suggested that in fact we increase coal usage so that the economic coal becomes scarce, and that's the only way to hit climate goals. Which I think if you consider that's a bit of a challenge. But my question is the following: my housemate during my PhD was looking at the energy return on investment and total life cycle carbon emissions, and he found that, so he was looking at the interconnector between wind farms in the Irish Sea and Liverpool and all that sort of thing, and he found that the vast majority in that instance of carbon emissions was coming from concrete pillars at the bottom, from overturning the seafloor bottom, overturning, like basically digging holes. My question is, in a situation of solar panels and concentrated solar and hydrogen, all these sorts of things, do you have an idea of the balance? Is it similar or different? Because of course you've also got interconnectors, but things at least on the surface and seem a bit less, heavy civil engineering.
Yes, we spent a lot of time trying to do EROI calculations. It sounds like your housemate was doing the right one and the one that we aspired to do, which is to actually calculate just the energy that's used. So many of them are bespoke calculations based on the financial return or the energy return, which will be very scenario based. So it's very, very difficult to build global models with really correct figures for the energy used in the process. And that, to be honest, your question, I think, is why I'm so happy to have come to work here, where the knowledge of the material processing and the kinds of the backstory to the kind of calculations that economists would make for this is there, so that we, if we want to, can actually pursue the story of where these things have come from right back to the beginning and really confront the question of whether there might be some cases where it's a false win. Yeah, and it's something I'm very conscious of, hence why I put up the slides about the trees, because that's one thing you can be sure is going to help. And also, I think the backing renewable energy where it's really going to get a very good energy return on investment is another thing that concerns me. Doing the calculation separately for every country might not be as hard as you might think, but it does require a bit of time, and hopefully in 2 years' time we'll be able to give a really good answer to the question.
Okay, Martin, do you want to turn to one of these questions on the Zoom? So there's one from Marcin regarding, again, other energy types and maybe even touching on technology. I thought that did Tesla not develop a solar tile that they can, or was that a real thing? It wasn't kind of a spoof. That was actually real. I'm reading and listening. No, go for it. I was kind of addressing the audience. And you can go ahead. Okay. So I guess from
I'll go in order. Marcin's question is a very good one. I chatted to, I found with the chief engineer of UQ who's addressing this question. The retrofitting, it's interesting, a lot of the cost of the solar panels now is just simply getting them up there and getting them on. And so, for example, that's what's stopping UQ literally carpeting its buildings in solar panels, is that it's not the panels that are the problem, it's the cost, which is why they go for an array on unwanted or cheap land. And this is a concern in a period where we really want to get people employed. I hope that we will find that it's still financially viable to employ the people to engineer these things on the essentially free space. But it's interesting that one of the problems in being in utopia like Brisbane is that people are very expensive because we use 100 kilowatts each. So the cost of installation is probably going up, and that is perhaps somewhere where governance can really make a huge impression. I should probably stop, otherwise I won't get to the next
question. I think we should touch on the last one and then...
Exactly, yeah, that's right. It's dangerous to ask me questions.
I realise that people on Zoom can't see the question. So for those on Zoom, there's a question from Rhys Davis, just touching on the energy density of uranium, and maybe we should be, again, reconsidering nuclear. That's right.
Well, nuclear, when we were looking at modelling the projected IEA forecast, the International Energy Agency's forecast, your nuclear doubles. So it is a huge component of this. And who knows, in the long run, it may in fact surpass. I guess the difficulty, the solar energy is just simply so abundant that it's very difficult to imagine that in the far future, we would really prefer to dig up uranium. So I suppose that's my perspective, having looked at the numbers stared at the numbers for quite some time. Whether we do go through a phase of, a third, say, or even a half of actually resorting to that will be interesting. And I wouldn't rule it out. But what I'm seeing from the research is that given the complexity and also the mining impact for uranium, the money at the moment would be on solar energy and a wide array of different storage mechanisms, some of them quite low tech.
On the uranium point, is it still true that the cost of decommissioning is excessive? In a similar, in many ways to mining, I suppose we don't really consider the true cost of closure, but to consider the cost of decommissioning a nuclear, is that? That's another thing that you can't, that the other solutions to the problem don't have such a legacy for. Although that is, this is a question that we can answer with the expertise in this institute. We can look at the better of the two evils. Would you rather have lithium and cobalt tailings dams everywhere, or would you rather have a smaller number of decommissioned nuclear sites? It's a very interesting question that if no one in the literature has sort of addressed that head on, it's something we might consider doing.